we're kind of mopping up our talk about antigens and antibodies and antibody-mediated immunity. We've talked about antibody-mediated immunity and how activation has occurred, activation of the B cells, and what happens. But we're going to talk a little more about antigens and antibodies. So we've got to talk about some terminology. The first thing would be antigenic determinant sites. And antigenic determinant sites are defined as the region on the antigen to which the antibodies bind. Okay, so it's the place on the antigen where the antibody binds. All right, we're going to talk about these here just in a little bit. We just want to get these terms down. A complete antigen is an antigen with at least 2 antigenic determinant groups or sites, I should rather say, and exposure to a complete antigen will lead to B cell sensitization and the immune response, which involves B cell activation and the whole deal. Okay, so that a complete antigen is required to get an immune response. So a hapten, though, is a partial antigen. A hapten is a partial antigen. It must be attached to a carrier molecule and in order to function as a complete antigen. And to trigger, not grigger, the immune response. Okay. So, what's an example? Well, your tissues have, oops, I'm going to make it smaller. Tissues have carrier molecules. They contain molecules that are able to bind to haptens. So this is what happens that, like for example, in penicillin allergies, in some people's tissues have these particular carrier molecules that will bind to the penicillin, and penicillin alone is just a partial antigen. But when it binds to the carrier molecule that certain tissues have, certain people, their tissues have them, it will form a complete antigen. So this example of penicillin allergy is an example there where one's own antibodies will attack cells, your own self, normal cells. Okay, so that is what a hapten is, and haptens can, in some people, then bind to carrier molecules, and that will actually cause allergic reactions and sometimes autoimmune reactions. Oh, here's a picture of an antigen, this yellow thing, and these little bumps on them are the antigenic determinant sites. All these little places are, and here are the antibodies, and the antibodies will bind to the antigenic determinant sites. So this is showing you antigens. Here, this whole thing's an antigen. These are the antigenic determinant sites, and this is showing antibodies binding to them to help neutralize them and take them out of commission. So there's a picture. There's a complete antigen here, and it's got at least two antigenic determinant sites, which then enables an antibody to bind to it. Here's a hapten, or an incomplete antigen. Here's a carrier molecule, so that this little guy fits right in here, and then he will now make a complete antigen and allow antibodies to bind to it. And why is this a problem? Well, here's the reason. Antigen-antibody complexes will produce these important effects, and they normally are good effects when you're trying to deal with a foreign invader. And so let's look at these. We've got neutralization, we have agglutination, we have activation of complement, we have attraction of phagocytes, opsonization, stimulation of inflammation, and prevention of bacterial or viral adhesion to surfaces or protein coating. So what these terms mean, again, you can look in your book and get a little bit better definition, but this just means that the antigen has been neutralized. It's been taken out of commission by the binding of antibodies. It binds to those antigenic determinant groups so that they cannot then bind to receptors on your cells, so they can't go and attack your cells, your tissues. Agglutination means that they will clump up by the help of the antibodies and will take them out of commission, will take those antigens out of circulation. When antigen binds with antibody, it will activate complement. And you remember what happens when complement is activated. We talked about that in the nonspecific defenses. And remember that antibodies have a place to bind complement. Remember up under the little arms, in the little armpit areas of the, it's not really armpits, but the little areas of underneath the arms of the Y of the antibody. It will cause phagocytes such as neutrophils and macrophages to be attracted to the area. Opsonization means the enhancement of phagocytosis due to these antibodies and antigens binding together. It will stimulate the inflammation process, which will help get rid of these antigens, and these antigen-antibody complexes will prevent the bacterium or virus to adhere to the surfaces of the body because they coat them. They form a coat around those antigens and will help. They will help prevent binding. Okay. So if we want to just kind of review antibody-mediated response, we'll remember that it's a two-part process. The first part is when first IgM is produced, and then IgG is the second type of antibody that's produced. Usually the antibody levels or titers will peak 1 to 2 weeks after the person has been exposed to the antigen. And that's called the initial response. That's what happens when we're first exposed to the antigen. Then the secondary response is when the memory cells will differentiate into plasma cells. So the second time, let's say a month or a year or 2 years or 10 years down the road, your body encounters that same antigen, you have memory cells still lingering in your body, and they will, once they see that antigen, they will quickly differentiate into plasma cells and produce high levels of antibodies very quickly. So the antibody titers or levels will increase rapidly. And this is the basis for vaccinations. This is a graph showing you that once you are first exposed to the invader, the organism, IgM, the blue, is going to levels will rise and then they'll fall. But as the IgM levels are falling, at this point IgG is being produced, and then it will rise and it will linger and then it will taper off after time. That's the primary response, the first time. Then let's say down the road, months, years, we are exposed to that same antigen. What happens is, of course, IgM is going to be produced, but because we have memory cells, the anamnestic or memory response is going to cause these cells, these memory B cells, to produce lots of antibodies. They're going to quickly differentiate into plasma cells and produce tons of antibodies so that you have an immune response very, very quickly, and that's what helps you fight that infection off much more quickly. So, if we look at an overview of this immune system, we see that we've got nonspecific defenses and specific defenses. The nonspecific defenses are going to mount a direct physical and chemical attack. We saw that before. We talked about our natural killer cells and our neutrophils and those kinds of things. And there also are circulating proteins. We talked about interferons and complement proteins. And then in our specific defenses, we have direct physical and chemical attack. Remember, we've got the T cells, our cytotoxic T cells, that will release chemicals and destroy the infected cell. And then we have attack by circulating proteins. In this case, these would be antibodies. So that's an important similarity between the nonspecific and the specific defenses. This is a great picture that kind of ties it all together. This is showing you your nonspecific defenses. This is showing you your specific defenses. And here's your antigen, and this is just explaining how all of this, the antigen will trigger specific defenses, the antigen will trigger nonspecific defenses. And this will just remind you of all the different things that the nonspecific defenses do. We've got a direct physical and chemical attack, and then we've got a complement system, and that sort of thing. Okay, so those are nonspecific defenses. And then our specific defenses, we have the cell-mediated immunity, and we have antibody-mediated immunity. And we've got the helper Ts that are important in both. The helper T cells, the CD4s, are important in both cell-mediated immunity and antibody-mediated immunity. So this is a really nice way for you to kind of look at this and review, and then see how these suppressor T cells are going to help control and inhibit this immune response to keep things in check and not go overboard. This is just a little bit larger. I could have used this to talk to you about it, but I didn't. And this graph is just showing you in a period of time what happens with respect to your nonspecific immunity and your specific defenses and all these little deals. This is the little labels are pointing to the different colors, telling you what happens. So this is very helpful, showing you how here you've got your nonspecific defense with your neutrophils, your natural killer cells, your macrophages. Of course, macrophages are important in your specific defense too. There, and then there's your cytotoxic T cells, this purple, and then we're starting to see here are our plasma cells, and they're going to be secreting antibodies. That's showing you your antibody titer. So all of these forms of immunity are going on, and they just happen, slightly different time frame. The nonspecific goes first, and then we've got the specific immunity happening. So as far as clinically speaking, we need to talk about autoimmune diseases, immunodeficiencies, allergies, and vaccines. And we will take this up in just a moment and in our next and final video. Thanks.